Okay, so regarding the vertical acceleration line, unless you're in zero gravity, and I would have to tell you, the effects of gravity can be neglected. You always have to pay the gravity mafia. And if you want to think about this in terms of a financial exchange, if you're on Earth, the gravity mafia charges $9.86 per kilogram. Okay? That's what the cost is. So, on what you did at the beginning when you had the scale and you had a half a kilogram mass, so if you multiply that by 9.8, you get 4.90 newtons. So the cost of doing business to pay off the gravity mafia is 4.9. So what you did when you accelerated it upward is that you had a bigger value than 4.9. Remember, the reading on the scale is the applied force. That's the money that you bring into the situation. Then from that, you subtract out whatever you have to pay the gravity mafia, whatever's left over, that's your net profit, okay? So, make sure on those ones where I tell you to make a sketch of a free body diagram off to the left, and there should be 3 of them on that front page, okay? So if you look at the front page, there should be 3 diagrams where you have force. And it's pretty simple. All you have to do is just say, hey, here's my force applied going up, here's my opposing force going down, and what changes, and hopefully this makes sense. So on number 10, you're moving at a constant velocity, which means your net force is going to equal to 0. On number 10, that's when your constant velocity is number 10. On number 11, you want it to accelerate upward. So that should make sense that your answer to number 11 is bigger than your answer to 10. So number 10, you're saying, hey, how much force does it just take to lift it? Then on number 11, not only are you lifting it, you're also applying the force to make it accelerate, okay? So that's why that answer to number 11 should be bigger than your answer to number 10. And both of them should start with a 5, okay? Actually, all of your answers on 10, 11, and 12 should all start with a 5, okay? So boom, boom, boom. Vastly different in terms of answers, but they all should start with a 5. On that back side, on page 2, answers 13 and 14 should both be something times 10 to the 4th. Okay, and hopefully it's the same situation. Hopefully you realize your answer to number 13 is bigger than your answer to number 14, because on number 13 you're making that helicopter accelerate upward. On 14, basically your gravity is helping you out, okay, so it doesn't take as much force. On page 3, you should have 2 different accelerations from that Atwood machine, okay? One is your theoretical, and that's oddly enough by taking your net force and dividing it by the total mass. And this is what gets screwed up more than anything. You have to divide by the total mass of the system, okay? As long as everything is moving, everything has inertia. Everything wants to resist a change in motion, okay? That's why you always divide by the total mass. Make sure on that you also have an experimental acceleration, and you're going to use 2x over t squared equals that acceleration. Okay, at some point, let me see that calculation of where you do that theoretical, maybe underneath those boxes on page 3 where you have your data. That would be a cool place to put that. Make sure you have explanations on 2, 3, and 4, okay? Just don't have the word different. So what you all did yesterday is that you had the track, boom, had the pulley, you have the 20-gram mass over here, okay? So here's what I want you to see, is that, oddly enough, it's force net equals force applied plus force opposing. So if you're on a flat surface, and this is a huge if you were on a flat surface and there is no friction, there is no opposing force. So what that means is your applied force is your net force. And the only force available to make this thing move is the mass of what's hanging down times g, okay? No matter what happens, your applied force in a situation like this is the mass that's gonna fall times g, okay? That's it. 20 grams, 10 grams, an elephant, doesn't matter. That's what's going to make the system accelerate. So, when you get to the next part, and this is what we're going to talk about today, which is inclined planes, you took a little piece of wood and you put that underneath the table. Now, this is what you want to think through. Did by adding that piece of wood underneath the table impact the applied force?
No.
No, because it's still 20 grams times 9.8. So your applied force remains the same. But now what happened is that now you have an opposing force. And we'll talk about this today, how this actually works. So basically what's happening is that this is a component of the gravity mafia. Okay? So basically what's happening is if you're on a flat surface, the table is balancing out the gravity mafia. It's like, hey, you're pulling it there, but the table is going, I got your back. Don't worry about it, the table is there. But once you put that on an inclined plane, now there's a component of that gravity mafia that's acting down the inclined plane. And today we'll actually see how we do that calculation. So this was just kind of an introduction, like, hey, do you understand the conceptual part of this? Okay. So let me give you some hints on some of those answers on page 5. So if you don't know how to do, like for example, that final set of questions on number 1, okay, go back and look at what you have done. So if you look at what's happening on number 1, you've got, and there's a reason that I specifically used, and this will make sense later on, I purposely put that 200 gram mass, excuse me, and that 240 gram mass up here. So here's what I want you to see is the difference. With this one, if I put the 200 gram mass here and the 240 gram mass up on the table, the 200 gram mass is going to fall and you're going to drag the 240 gram mass with it. Okay, so if you put it on a flat surface, 200 gram mass falls, 240 gram mass stays up here. But if you put that on an Atwood machine over a pulley, then the 240 gram mass is going to fall and the 200 gram mass is going to go up. So in both situations you have the exact same mass, 240 and 200. If you're on a flat surface, I'll put the 200 gram mass there, it falls. On this one, if I put the 200 gram mass on one side and the 240 gram mass on the other, the 240 gram mass falls, and the 200 gram mass goes up. So what's the difference between the two? Why in one situation does the 200 gram mass fall, and the other situation the 200 gram mass goes up? Elliot?
First normal.
What about it?
Table.
Yeah, exactly. So what's happening here is the table is balancing out the force of gravity trying to pull it down. So is gravity pulling down? Absolutely. But the table is there, and that's providing that normal force. Whereas if on the string, it has room to fall. That 240 gram mass has room to fall because there isn't that normal force to balance it out. Okay. So your answer to number 1 on page 5 with that situation, you would get a very, very, very good weighted GPA.
Okay, question. For number 1, is that kind of like how our force net should just be?
Whatever, again, there's no friction, your force
It's just, yeah. Okay.
is just 200 grams times 9.8 meters per second squared. So that's it exactly. So on number 1, you're going to go, your force applied is the same as your force net, because of the fact that there's no opposing force. Now, here's a common misconception. Yes, you're dragging the 240 grams, but the 240 grams is not an opposing force. Does it have mass? Absolutely. Does it have inertia? Absolutely. But it's not an opposing force. How we take the 240 grams into account is when we take the force from what's hanging down and you divide it by the total mass of the system. That's where that's taken into account. Because that 240 gram mass is sitting up there going, dude, I don't want to move. Seriously. You want to make me move, you got to apply a force. So that's where that becomes a factor. Okay? Now, on number 2, I'm saying, hey, and this is going to be part of the labs that you're going to do, like, to get ready for the test. By the way, if you really want to plan ahead, the test over this is going to be a week from Friday. Okay, so that'll be the big forces test. So a lot of times when you get into like kind of the advanced classes, you're not worrying about numbers, you're worried about a mathematical relationship. So here's how you can check your answer on number 2 on page 5. You should be able to give what you have to anyone else in this room, and they should be able to take your equation that you have on number 2, and they should be able to take any set of masses, okay, on any kind of flat surface and get an answer. Okay? So obviously you have 2 different masses. You have the mass from the end of the string and you have the mass on the table. If you want to call it mass 1 and mass 2, cool. Mass A, mass B. Mass hanging, mass on the table. I don't care. But make sure that I know which those are. You just can't say, oh, M times G. I don't know which mass that you're using. Are you using the mass that's on the end of the string? Are you using the mass that's up on the table? Are you using the combined mass? I don't know. So here's kind of a check. Could you take your answer to number 2 and the information that I gave you on problem number 1 and use that information and get your answer to number 1? Okay? Could someone who has a generic basic understanding of mathematics and physics take your equation on number 2, look at the information on problem number 1, and get that answer that you have? Okay? So don't look at it through your eyes. Look at it as someone's like, hey, I don't know what's going on. Could someone who can read and understand the concept of mass come up with your answer to number 1? Kind of one way to think about it. Now, on number 3, here's what's going to change on number 3. Now there's friction. So listen to me, listen to me, listen to me, listen to me. On a problem like this, when there's friction, that friction only occurs between the block that's up there on the table and the surface. This mass out here is not affected by friction because it's not in contact with the surface. So when you do mu times force normal equals force friction, this force normal is only the mass that is on the table. It is not the combined mass. Okay? It is not the combined mass. It is only the mass that's up there on the table. So, on number 3, when you're trying to find the value of the frictional force impeding the motion.
Hey, Barry.
What's up? That answer to number 3 should be around 0.2. Okay? So your answer to number 3 on page 5 should be around 0.2. Okay? So here's the basic idea. Is that what's happening is that you've got this about 2 Newton force trying to pull it down. You have an opposing force of about 0.2 newtons. So if you put this in human interaction terms, not only are your mom and dad making you take your little brother on the date, your brother doesn't even want to go. And he's like laying on the floor and you have to drag your little brother. And now there's friction between you and the little brother and the floor, okay? So not only do you have to make him move and overcome his inertia, now you have to overcome the frictional force to make him move. Now, you should see that your answer to number 4, when you get that acceleration, should be around 4 meters per second squared, okay? Your answer to number 1 is around 4.5. So here's what I want you to see, and hopefully this makes sense, is that acceleration on number 4 is less than your acceleration on number 1 because of the fact that you have to overcome that force of friction. So some of that force, which is pulling down on that 200 gram mass, some of that force is being used to pay off the frictional mafia that you didn't have to worry about before. Okay, so that's why that acceleration on number 4 is less than your acceleration on number 1. Okay, does that make sense? All right, that's it. Any questions?
Yeah, I'm still kind of confused on 4. Like, how to find,
4
like,
on
is the
which
net
one?
force just, what?
On number 4?
Yeah, like, is it just you add the force applied?
Yeah, so
Plus
so
the
so
force
the
friction?
force is
Like, are
trying
they
to
the
make it
same?
move.
Okay.
If you look at force net equaling force applied plus force opposing, okay? So that's about 2 newtons, which is the
Yeah.
200 gram mass times g.
Yeah.
So your frictional force, which is acting in the opposite direction, make that negative like 0.2 newtons, which is that answer from number 3.
So they're not both negative?
No, one, you have to define, if you make them both negative,
Well, yeah, that's what,
then they're both going in the same direction. You would be saying friction is helping you out.
yeah.
So I always just make that applied force be the positive value, and then make that frictional force be the negative value.
Even though it's like gravity, it doesn't matter, because
No,
you make it, you make
if you
it.
want to make this a negative number, then make that the other one a positive. It doesn't matter.
Okay.
You just have to be consistent on how you set it up.
Mm-hmm.
Because here's the fundamental idea is that gravity is trying to pull that thing in one direction, and the frictional mafia is in the opposite direction. So you can make, I don't care which one you make negative and which one you make positive, it doesn't matter.
Yeah.
Just pick one. But then you have to be consistent on how you work the problem. Okay?
Thank you.
All right, anything else? The rent's going twice sold. Put that hinted in.
Mr. President,
But,
when I come in for my quiz, can I get home quiz? Because there's some of it that I don't understand.
yeah,
Hey, Bird.
Like, I
what?
have all the stuff from when I was here done, but it's like some of the ones from when I was gone.
May I contemplate?
Yeah.
What's up? Can I see what I got on my quiz again? I just wanna see if I miss only that one.
Now what?
If I only miss like one question.
What about it? I don't know what you're asking.
How much was the multiple choice question?
One
Oh,
point.
Oh, there's multiple choice on it?
So I said Luis.
So that's what.
I wanna know what else I
You
did.
remember what you
So
got?
I only thought I got the most quick one.
You got rejected?
No one. Bro, I didn't get rejected, bro. You got rejected.
But you missed 2 multiple choice questions.
Oh, I missed 2.
That one and that one.
Oh, yeah.
Told you, Louis. You had to have missed something else.
You're right. I don't remember what the first one was. Ooh.
Okay. So here's kind of the last big thing on forces. And that's inclined planes. So if I take this and put the card on there, come on, here, stay there. So you could actually kind of show the concept of inertia. So if I slide the track back and forth, what does the cart do?
Thanks.
Goes the other way.
pretty much stays in place, right? Okay? Because without an outside force, what does the cart do? Stays at rest, right? So if I do this to go back and forth, so there's pretty much not a lot of friction, so it pretty much just stays there. So if I put this down, and it's completely flat, like most of Kansas is, nothing happens. Now, does nothing happen because there's no forces acting on it, or because all the forces add up to zero?
All the forces out of zero.
Yeah, all the forces add up to equal to zero. I got gravity pulling down, which in this case is about 5 newtons, and then I've got an upward force of about another 5 newtons, okay? Everything adds up to equal to zero. But if I give this a little bit of slant at all, what happens?
Goes the other way.
What do you get? You get an acceleration, right? Okay? Now, I won't do this because it'd be boring and we all know what the outcome is going to be. But hypothetically, if I said, okay, class, we're going to do the easiest lab in the world. You're going to set up an inclined plane, and for the next hour, you're going to hold it up, and you're going to let go, and you're going to observe what happens. Every time, which direction is it going to move?
Down.
Down. If you let go of it and it begins to move up, something has gone horribly wrong, okay? So this force that acts down is oddly enough parallel with the surface. Not very clever, but this is what we call force parallel. So force parallel acts down the inclined plane.
It's really cool.
Now, the surface still has to be here. Gravity is still pulling it down. So the surface is providing a force to keep this cart from falling down. That's going to be the normal force. So now we're going to have 3 forces. Gravity, the normal force, and the force parallel. If I make this steeper, what happens to the amount of acceleration?
It increases.
It increases. So there's a direct relationship between the angle and the acceleration, right? As the angle gets steeper, the acceleration gets bigger. Okay, cool. So what we're going to look at is a little bit of geometry, just a little bit. So on an inclined plane, and let's make this, I don't know, 30 degrees. And let's say the mass is okay. So your gravitational force is the same as you've always done. Fg is just mg. Now, you're going to use this to calculate everything else. Do not make this a negative number. This is just a gateway value of force, okay? This is just straight up, get the number. Do not make Fg negative. It's just going to make things much more complicated later on. Just get the number, okay? So in this situation, I'm going to take 1.02 kilograms times G, and trust me on this one, you're going to get 10 newtons, okay? So the gravitational force is going to be 10 newtons. Now, if you were on a flat surface, what would the value of the normal force be? 10 newtons, right? Because it just sits there, it's flat. They balance each other out. Not true on inclined planes, and I'll show you the geometry here in just a second. Now, at this point, I want to show you a couple of different ways how you can draw these vectors. Both have their advantages. Pick the one that makes the most sense to you. So, obviously the track has to be providing a force to keep this thing from falling down. That's going to be the normal force. So one option is that you draw the normal force at a right angle to the incline like this, okay? Because that's what it's doing. It's a right angle to that surface. That's what's keeping that thing from falling in, okay? Then you also have a force, obviously, that's acting down the inclined plane. And that's going to be parallel with that surface up there. That's what we call it, the force parallel. Okay? So then you draw that one like this. So there's your force parallel. And that makes that a right angle. Now, if you go through the geometric proof, like alternate interior angles and all this other stuff, what you realize is that whatever angle this is between the horizontal and the incline, that's what that angle is going to be. So if that was a 45-degree angle, that would be a 45-degree angle. If that was a 3-degree angle, that would be a 3-degree angle. They're the same, okay? Now, this is where we've got to go back to do trig functions for just a second. So the gravitational force is the hypotenuse of that triangle. That's the one that you will always know. That's the bedrock, because you're always going to know the mass of the object. Knowing the mass of the object, you can find the weight of the object, okay? That's your bedrock. Start with this. So, if you look at that force parallel, and I know that angle in here, Louise, what trig function can I use knowing my hypotenuse, the angle, and I'm trying to find the side opposite? Sine, cosine, tangent.
Sine.
Yeah. So I know the sine of the angle is going to equal the side opposite, which is force parallel, divided by our gravitational force, okay, which is like the hypotenuse. So then your force parallel is going to be Fg sine theta, okay? Don't have to think, boom. And if you really want to get fancy, you could write that as mg sine theta, okay? Because that's fundamentally what you do. Is you take the mass times g, or you can just do it a separate calculation. So Louise, since you're on a trig roll, if I used sine to find the side opposite, what could I use to find my force normal?
Cosine.
Yeah. So then the cosine of theta is going to equal the normal force over Fg. So then your normal force equals Fg cosine theta. So remember when we started, I said, hey, I'll show you where this equation comes from. This is where the equation comes from. Okay, it's a geometric function. So if you're on a flat surface, what's the cosine of 0? 1. So force normal just equals Fg. Now, if you're on a flat surface, what's the sine of 0?
0.
That's why there is no force parallel if you're on a flat surface, okay? But this is why force normal equals Fg. Now, if you were to draw a graph, I'm not worried about the numbers, I just want the general trend. This is the angle. And this is 0 degrees, and there's like 45 degrees, and there's 90 degrees. And this would be the acceleration on an incline, okay? So, there's what I want you to think of. So, I've got a track, it's flat. What's my acceleration going to be?
0.
0. If I lift it up a little bit, I get a little bit of acceleration. I lift it up further, I get more. So the steeper I go, what happens to the acceleration?
Bigger.
Bigger. So what's the graph going to look like?
The sloping line up. It's a straight line.
Something like this,
Yeah.
Yeah.
okay? Now, if I go to 90 degrees,
Might have been.
what would be the acceleration of the car?
9.8.
9.8, because what's the only force acting on it at that point?
Gravity.
Gravity. So, if you go to 90 degrees, that acceleration is going to be 9.8 meters per second squared. So the steeper you go, the bigger the acceleration. That also means the bigger the force, because you can't increase acceleration without increasing the force. Okay, cool. Now, let's talk about these forces. No matter what happens on an inclined plane, whether there's an applied force, whether there's friction, doesn't matter. There's three forces that will always be here, no matter what. Your parallel, your normal, your gravitational force, okay? You cannot get away from those three. Those three are always going to be there. Now, the force parallel is just a component of the gravitational mafia. It's just like a sub-game of the gravitational mafia. It isn't the full-on, hey, this is what we have to overcome, but it's a component of it. Now, so there's a couple of things about force parallel. Number one, force parallel always acts down the inclined plane. If you're out in Colorado, if you've ever been snow skiing out in Colorado, you get off the lift at the top of the mountain, which direction is gravity always going to make you go?
Down.
Down, okay? Gravity, when you get off the chairlift, is not going to push you up the mountain. Like you get off, like, oh, which way is gravity going to make me go? Oh, I don't know, got to be prepared for both situations. No, okay? You know gravity is only going to act down because that's the easiest path for Mother Nature to take. If it was easier for Mother Nature to push you up the hill, that's what Mother Nature would do, okay? She doesn't, it's like, hey, let's make you go down the hill. So skiing is just nothing but force parallel. Okay, that's all it is. Skiing is just force parallel from a physics perspective. Now, here's another way that you can draw this, and this is a personal preference thing. So, one option, like we're going to have this 3-degree angle. If you like geometry and you like triangles, you go FG, and then you draw this as a triangle. So if you like triangles, like, oh, Mr. Burkett, I live for triangles. Cool, okay? Draw it this way. Now, if you're going to draw it this way, make sure your parallel is parallel with the surface. That's why it's called force parallel. Make sure the normal force is at right angles to the surface. Do not draw your normal force acting straight up. Your normal force is not acting straight up. Your normal force is acting at a right angle to the surface. Now, if you're on a flat surface, normal force does act straight up. But if you're on an incline, the normal force is going like this. So option number one, how you can draw your forces. Draw it as a triangle. If that speaks to you, cool, nice. Now, your other option, and this is more what actually happens, is that you draw your gravitational force acting down, cool. Then you draw your force parallel, acting parallel with the surface, because that's the direction, that's actually where it's going to happen. Okay, that's where that force parallel is going to be. And then the normal force is acting up like this, okay? So it's still the exact same geometry. That force parallel would have been here, that normal force would have been here. All I did was change the location of the vectors, okay? So this is more true in terms of where the forces are actually acting, because the force parallel is making it drag it this way, the force normal is going like this, gravity is acting straight down. From the physics perspective, this is more realistic. That makes the geometry work out. Now, keep in mind, when you look on your equation sheet, what is not listed on your equation sheet is that force normal equals Fg cosine theta. Force parallel is not listed as Fg sine theta. The only thing you have is F equals ma. That's all you have, okay? So you have to find a way the geometry, whatever, to know that, oh, FG sine theta is force parallel, FG cosine theta is force normal, okay? Because those are not listed on your equation sheet. Okay. Now that we have all that, so stop that camera for a second.